So if you're keeping track, we have 2 more lectures after today, so the quarter's almost over. So today we're going to dive into the beginnings of PC board layout. We're going to kind of go over some of the terms on what, the terms for printed circuit boards, or PCBs, and then we're going to start looking at Layout Plus, the design software you'll be using for the actual layout. Just one quick announcement. My office hours this Thursday are going to be in the morning from 10 to noon instead of in the afternoon, just because I'll be out of town this weekend, but I'll still have email afterwards. Are there any other just general questions or announcements otherwise? All right. So let's talk about layout. So layout is basically the transition from a schematic, which we've seen over the past couple of lectures, into an actual printed circuit board that you can see in the real world. This is the end goal. This is the product that you're making, is the actual circuit board itself. So the layout process will take all of your schematic, and it'll take all those net lists, it'll take all the connections you have, which again were called nets, and convert them into air wires and then eventually into a circuit board. So that's what we're going to kind of go through. So printed circuit boards usually have multiple layers of copper. You can have a single-sided board, although it's pretty uncommon. Usually you'll have double-sided or 2-layer, which means you have copper on the top and the bottom and some epoxy or laminate substrate in between. And then each layer of this copper has some patterns on it, and the patterns are what actually route your signals, between components. Or you can have large copper areas, which are called pores or planes, that connect power and ground together, for example. So if you have very large signals or high power signals, you'll either have a plane layer, which is an entire layer dedicated just for that signal, or you'll have just some pore, which is a large region for that signal. And the big thing about layout is to think in 3 dimensions. It's 2 dimensions in that you're laying these traces across your board, but there are multiple layers where you can have these connections. And so there are things called vias that allow you to change layers. So make sure you think of everything in 3 dimensions. Don't forget that just because you can't get directly from point A to point B on the current layer doesn't mean that you can't just drop down to some other layer and go across. So keep the 3-dimensional perspective in mind while you're working on this project. So we're going to do a 4-layer board for your project. 4 layers makes your life easy. If you did 2 layers, it's much harder. So this is a good thing, not a bad thing. But just to give you an idea, current PC motherboards have 6 to 8 layers on them, at least in general. The development kit that you guys have been using at the beginning of the quarter is 2-layer. It's just double-sided. So it kind of spans everything out there. You can have boards with tens of layers if you need to. And as far as technology goes, there's something called flex PC boards, which are kind of flexible. They're put on something kind of like Kapton or something like that. And the current state-of-the-art for that is 50 micron trace widths and trace spaces, and they'll have dozens of layers on a single one. And that's used in a lot of consumer electronics. So any questions on kind of what layout is? So this is the transition from the schematic into the actual board. Yeah?
How does price grow with number of layers?
All right, so how does price grow with number of layers? It depends on your manufacturer. Advanced Circuits, who our research group has used for a lot of our boards, has some specials online, and it's $33 per board for double-sided. No quantity restrictions if you're a student. So you can buy just a single board at $33. A 4-layer board is $66 from them. Now, if you get to a whole lot of layers, it will grow a little bit faster because it makes it a little bit harder to get your yield. But it's generally linear or slower.
And are there size constraints?
Yes, there are size constraints in circuit boards, and it depends on the fab company. The fab company we used had something like I think it was about 14 inches by 24 or something like that. So it's a pretty large board, and in general your boards will be quite small comparatively. All right, so let's go over some just basic terminology for printed circuit boards, or PCBs. So first off, there's something called a trace, and the trace is this actual copper connection that connects your pins and vias and whatever you have on your board together. So a trace is kind of analogous to a wire on a proto board. So this is what actually carries your electricity between different connections. Now we also have layers, and so layers are basically unique levels on your board. And so the layers that we've already kind of mentioned before are of copper. So you have a top layer and a bottom layer, so that's the top and bottom of the board of the copper. And then oftentimes you'll have a power and a ground layer inside. And then maybe you'll have inner one, inner two, however many different signal layers you need. So the top and bottom is where you can put your actual components because it's on the outside of the board. And then the power and ground and inner layers are all inside the board, so that's only for traces and vias. So there are other types of layers as well that are important. So most notably you have solder masks. So if you look at the circuit board that we have, it's green, right? And it's green because of the actual solder mask. It prevents solder from connecting from when you're soldering components on to the entire trace. It just connects at the actual pads. If you don't have a solder mask, the boards generally are kind of a brownish yellow color. And the traces are silver, as opposed to being just darker green and lighter green. There's also something called silk screen. So silk screen is like the legend or text that you have on your board. So you'll notice that your boards have a white silk screen, and that has all the component labels and things like that. And both the solder mask and the silk screen you can have on the top and bottom, or just one side, or what have you. For you to have a silk screen, though, you have to have a solder mask. So the silk screen only prints on top of solder mask. Then there are also some other layers inside of layout that we're not going to talk about, we don't really care too much about, like an assembly drawing or fab drawings, which are if you have automated robots placing all the parts on your boards for you. There are also drill layers, which tell the assembly equipment where to drill the holes and vias for your components. But that's something that we're not going to have to directly address in this class. So then there's something called a via, and a via basically will connect traces or copper areas on different layers. So it's basically a hole that's drilled through your circuit board, and the edge of the hole inside is coated in copper. It's plated. And then that connection actually goes out to the trace or plane that you're connecting to. So vias are what you use to transition between different layers of copper. For the designs that we're doing in this class, and for most of the designs that you all will do, at least to start with in the real world, the vias will go all the way through your board. So once you drop a via, you can access it on any layer of the board. And that's important because it makes the assembly process much easier for the PC board fab company, because they can stack all the boards together, laminate them, and then plate the vias all at once. There are also things called blind vias and buried vias, which only go between certain layers and they don't connect all the way through your circuit board, but that makes your boards a lot more expensive and a lot harder to fab. So unless you're doing high-end consumer electronics, you won't be using blind or buried vias anytime soon. But they do exist. So we also have pads, and pads are basically an area of copper where you actually connect something. So you'll have a pad for all the surface mount devices, and the pad is the actual electrical connection you solder onto. You also will have pads around drill holes and around vias, which is the copper that goes from the hole to the actual copper layer. And we also have something called the pad stack, and the pad stack basically defines a whole bunch of settings on each layer for a given pad type. So for example, if you're going to make a via, the via will have a type inside the pad stack, and you'll have to define how big the drill is for that via, the diameter of the drill. And you'll also have to define how much copper you want to have around that drill on each layer. For example, if you have power planes inside, you may want to have heavier connections to those power planes, whereas on the outside you may not really care so much about the current flow. If you have surface mount components, so if you have the chip like the resistors and capacitors and even ICs that are on your development boards, you'll notice they sit on top of the board, they solder onto a pad, the pad goes off in the trace, and that's it. So the pad stack for that component will have information inside the top layer, which is where the actual pad is that you solder to. It'll have information on the solder mask layer for the top, telling it where not to put solder mask around the pad. And it'll have maybe some silkscreen showing the outline of the component. So if you look, all the components on your board are outlined like the resistors and capacitors. But for example, on the drill layer, or the bottom layer, or the inner layers, there's no information in the pad stack for these surface mount components, because they don't affect those layers. Does that make sense? If you had a through-hole component, like your LCD screen or your keypad, that actually has drilled holes all the way through, there's information on every layer in the pad stack for that component. Because you have a drill hole, and then on your inside layers, even though you may not be using the inside layers, you still have to specify the maximum copper around it. If you don't have plated holes, it generally costs a lot more from your PCB fab company. So you're generally going to have to break these out into each layer.
So can you
Yeah.
explain a little bit more about the relation between the solder mask and pad? So
Okay, so the question is, what's the relation between the solder mask and the pad itself?
yeah.
So the pad in the copper layer is where you're going to be soldering to, right? So you don't want there to be solder mask covering that up because that's the one part you actually want exposed for soldering. So on your solder mask layer, you'll draw an outline around the pad, and it's a negative layer. So anywhere where you draw that outline, there'll be no solder mask. And so you'll draw a layer that basically matches the pad in copper for your solder mask layer. Now, different fab companies have different tolerances, and they have different tolerances for all of these things and everything that's on the next screen. So there's something called solder mask swell, which is kind of how much it will expand and then impinge upon that pad itself. So there'll be some spacing you need to have to keep the solder mask even further away than the pad to guarantee it doesn't get covered. But if you look at the development board that you all had, if you look closely, that you can see the very fine line between where the green ends and where the actual silver of the pad begins. So that's the difference between the solder mask and the pad itself. Yeah.
In the board that we have given, we can see very large areas of solder
Of
the
co-
traces. Some of the places are very huge in area.
Right.
So one of those, and they don't look like traces actually. They look like pretty big areas.
All right, so the question is that on the development board, there are areas that have a lot of copper, but don't look like they're traces necessarily. So you can use these copper pores for various things. So under your LCD panel, for example, you'll see a very large square kind of coming out, or a rectangle, and that's using the copper actually as a heat sink for your voltage regulator coming off the tab. And then throughout the rest of your board, we flooded a lot of the area with ground in between the traces, and that helps decrease your signal noise, which we'll talk about later on. So any other questions so far? So the last PCB term on this slide are air wires, and air wires basically indicate the connections between pads that you haven't yet routed. So this is what you're going to convert into traces. So when you first start up layout and you have your Netlist, which you imported from Capture or from Design Entry CIS, so you have the nets that you created inside your schematic. They'll all show up as air wires, as actual physical lines showing you what pads have to be connected together. And then as you go through and route them, which I'll show you all later on today, you'll actually see them disappear, and you'll have traces on your board. So air wires are what you start with, and you convert air wires into traces. So any questions on these terms? All right, so here's a little graphic with a few more terms on it. So on the left-hand pane here, you'll see basically a top or bottom or a positive image. So this shows that everything in black is copper and everything in white is not. Over on the right-hand side, we have a negative image, so this is going to be like a plain layer inside, but the same thing still holds true, that the black is copper and the white is not. Now inside of the tools, though, you'll see that a lot of times it'll be inverted, so you'll see traces inside of here, and then what you send to the fab is actually a negative image of those traces. So there are a couple that I want to point out in particular. So these are tolerances, and again, these will vary depending upon your board manufacturer, and I'll give you all a list of your tolerances for the project that you have to meet. So first off, there's a track width, which is the actual width of the trace, and then there's a track-to-track spacing. So for example, for Advanced Circuits, which is the company we use, you can have an 8 mil width and an 8 mil space at no extra cost. And if you need smaller, you can go to 4-4. So 4 mil width, trace width, and 4 mil trace spacing. And a mil is 1,000th of an inch. It's not a millimeter. So a mil is 0.001 inches. Now, some manufacturers will have differences between the trace to trace versus the trace to pad, which is up here, or the pad to pad spacing. So these are all copper spacings. In general, they'll be about the same. Now up here in this left-hand part, you'll actually see these two holes that are going through. So these are either holes for a component or vias. And you'll notice there's something around it with copper. So you actually have to connect from that plated wall inside of the hole up to your layer, which is this what's called the annular ring, and that goes around it. There is a minimum annular ring diameter or width or increment that on top of the original radius or diameter of the drill. So a lot of times this will be at least 5 to 10 millimeters, 5 to 10 mils, depending upon your process. So again, all of these parameters are going to be process specific, but these are the names that they're going to generally be assigned. For us, we're not going to care about mounting hole versus tracks because we're not going to have any non-plated holes. But you do care about the trace to edge of the board spacing or drill to edge of the board because there are stricter tolerances on that to make sure that when they shear your boards or dice your boards, they don't run into your actual traces. Now, one thing that you'll notice on these inner layers is that, for example, right here we have one hole, and there's copper right around the hole, and then there's a big gap, and then there's the plane. So this would be a via or a component hole that goes through the plane layer but does not connect to it electrically. You still have to have this copper around the actual drill so that they can plate the hole later on, but it doesn't actually connect through. So you'll notice that that means there's quite a large space here that you cannot use in this plane layer between vias or between component holes. Now in this upper left hole, you'll notice that there's still that annular ring around the hole as is required, but then there are these little spokes coming off into the plane. So this via or this component hole will be connected to the plane layer. And the reason why you don't have copper in these white areas is what's called a thermal relief. So this copper is a lot of copper, and if you're trying to solder something into this component hole, if it's a component hole, it would take forever to heat up the board enough to melt the solder around here. But since we have these tiny spokes going off, and these are generated for you automatically, this is not something you have to do, you only have to heat up basically the annular ring plus some gradient across these spokes before you can solder, so it's much easier. If you do not have these thermal reliefs, it's nearly impossible to solder. Trust me. Question?
Are mills standard units, or does it vary from manufacturer, whether you're in imperial or metric?
So a mil is a standard unit for PC board fab. Some companies will go in millimeters, so it just depends. But basically everything that we're going to do will be in mils, and if you have metric parts, you'll have to convert them to mils. But mils and millimeters are the two different standards, which unfortunately sound a whole lot alike. But they're very different. Components made, if you have a millimeter component and you accidentally interpret it as mils, they will not fit every time. So any other questions on these terms? Yeah?
Why do we need that copper layer in the bottom left? Is it annular ring?
The copper layer here?
No, on the right.
Oh, here?
Yeah.
So you're required to have an annular ring around every hole that's plated. So the boards are actually fabricated by imaging out your copper traces, your copper layers, and then they laminate all the layers together, and then they plate the inside of all of the holes with copper. And for the plating process to work, you have to have copper nearby. And so you're required to have this annular ring near all of your vias and all of your component holes, whether or not there's an electrical connection on that layer. So any other questions? So the annular ring is a minimum width of the ring required. If it's any thinner than that, they can't guarantee your holes will plate, and they yell at you. But you can have the annular ring as large as you want. Yeah?
So I think you just mentioned that if there's all those small connections between the annual ring and it's a large copper area, it will be very hard to solder. So how do you deal with the bottom example where there knows that
Right here?
Yeah, there's no connection to the
All right, so the question is, since it's so hard to solder if you have direct connections, how do you deal with this bottom example? So on this bottom one, remember that the white is where there's no copper. So you have an annular ring just around the hole, because this is the hole that you drill, and this is the ring itself. And then this white part has no connection. So you can solder just fine to components on the other layers, on the top and the bottom through this hole, because it's not sinking the heat into the copper. On this one, you have the no copper just around these small parts with these small connections going out, and this allows you to solder in this hole, right? Because it allows this inner annular ring to get very hot before you wick away all the heat into the plane layer. If you just had this whole thing filled with copper right here on your hole, then you're going to sink all of the heat away, and you'll have to heat up this entire region to the melting point of the solder before it starts to connect. Whereas when you have these little spokes, you just have to get this ring heated up to the melting point of solder, and then there'll be some gradient of temperature across here, but it's much easier to obtain with much less energy than if you have to heat up the whole board.
I mean, for example, you want to solder directly.
So when you have this connection here, so the white part in the center is the actual drill hole. So anything that you put through this hole right here will connect to this plane layer, because black is copper. Anything you put through this hole, because the white is the drill hole and the black is the actual ring, anything you put through this hole you can solder, but it's not connected to this layer. Because remember that this view is just one layer of many on your board. So just because it's not connected on this layer doesn't mean it's a worthless via or hole to have. Does that kind of answer the question?
Why
Yeah.
would you want to put something into the VI? I mean, there would be paths to...
So the question is, why would you want to put something in a via? And you don't, unless you're debugging a board. But you will need to put stuff in component holes if you have through-hole components. So if you look at your development boards, the LCD, the keypad, and the battery backup, and the power connector are all through-hole components. So they have holes, and the only difference really between a hole and a via is what it's used for. But mechanically it's basically the same thing, except vias are usually very small. So you generally are not soldering things into vias. They are handy to have for debugging, though. Yeah?
So if this layer is just in between, then how do we get solder?
This layer?
Yeah.
So this is a layer in the middle of your board, and the question is, how do you get the solder into it? So you have holes that are drilled through, and these holes are plated. So if this was a component hole right here, right? The entire hole itself is plated in copper. And you remember that you have to have this annular ring on every layer. And so when you come out to your top layer or your bottom layer, whichever side you're soldering on, there'll be an annular ring as well. And so your lead would be sticking through the hole, and you'd solder onto this ring just like you normally do. But it's electrically connected because the inside wall is plated in copper to this layer as well. You cannot put component inside layers.
Yeah, sure. So basically, when I put solder on the top, then it will go all the way down.
When you put solder on the top, it will wick in, but even if it didn't, it's fine, because the inside wall is plated in copper. The black is copper here, so they make this black trace, they drill the hole, and then they plate the inside of the hole with copper. So there's electrical connectivity even without you soldering. That's how vias work, because vias have no solder inside of them, except whatever is left over from plating. Yeah?
Just generally speaking, first of all, is track, the term track is linked to a trace.
Yes, so track and trace are the same thing.
So I understand these traces are carrying signals back and forth from point A to point B. What would be the point of creating a whole for this?
Okay, so the question is, it's clear that these traces are carrying current or electricity through from point A to point B along the trace. So what's the point of having an entire layer that's just one signal? So this is most useful for your power and ground. So you're going to need to have, for example, VCC, which in your case for your development, for your project will be 3.3 volts. And you're going to need to have ground going to a whole lot of different places on your board. And it's the same signal going everywhere. And by having an entire plane layer, first off, it's very easy to route to, because just about anywhere you are, you can just drop a via to this layer and you magically have ground, and you don't have to route a connection. And it also, you get a capacitance between these two plane layers, between the ground and the VCC, that helps keep your power rails higher. It helps bypass. So that's just kind of an added benefit that you get from the two plane layers being close together. But in general, your plane layers are going to be for a signal that's distributed to many places like power and ground. There are very few other signals that you would have a plane for. Yeah.
So if you're requiring to have an annular ring of non-copper, then how do you connect?
No. The annular ring is copper.
Right, never mind.
Yes, the annular ring is copper. On both of these drawings, black is copper, and the annular ring is the black part. Yeah.
For sort of small one-off projects, how do you solder surface mount components by hand?
So the question is, for small one-off projects, how do you solder surface mount components?
Magic.
Yeah, magic, very carefully. You can do it by hand with a soldering iron. It's not a problem. In fact, all of your boards I assembled by hand. So practice.
And moreover, is it not the case that if you want to route problem ground, there is voltage drop, and to avoid that or to keep that to minimum, we use large areas of
That's correct. So there is a voltage drop across every trace that you have current flowing through. And so the thicker your traces, or at the extreme having an entire plane layer, will help reduce that voltage drop because it reduces the resistance. So it's a good thing to make your traces as wide as possible, or to use plane layers for these high power traces. Yeah?
How small the track width and spacing is there before you start working on it?
All right, so the question is, how small of a track width is there before you have to worry about power? It depends on how much power you're putting through. So for example, on our buoy system, we had 40 amps going through a trace, and no matter how wide your trace is, the trace won't handle it, so you have to solder on wire on top. If you're talking about, a very high voltage, type of trace, you may have to worry a bit more about the spacing so you don't have arcing. So it depends on your application. For, stuff like we're doing, if the biggest thing you're driving is like an LED, that's maybe 10 or 20 milliamps, you can get away with an 8 mil trace in space, no worries at all. For your power traces, if you opt to do a 2-layer board, you'll want your power traces to be larger. Because like going into your microcontroller, you may be dissipating a couple hundred milliamps. And coming out of your voltage regulators, you'll probably be sourcing a couple hundred milliamps. So unfortunately, it's track dependent. So any other questions? All right. So the next couple of slides are basically written tutorials of what we're about to do. So the first thing that we're going to do when you actually do a layout is you're going to create a netlist. And the netlist is created inside of Design Entry CIS, and it basically is a file that has a listing of all of the nets you've created, so all of those lines you created in your schematic, and of what nodes or what parts are connected together through those nets. And again, we'll go through this in an actual demonstration, but this is so you have a written copy somewhere. Before you actually start your layout, you need to make sure you have footprints for all of your parts already available. That's very important. If you don't have your footprints available, it's going to kind of crater in the middle of creating the layout, and you'll have to start over and then re-import all your parts. So make sure you create your footprints first, and then begin your actual layout. And we're not going to create new custom footprints today. We'll do that probably next class, depending upon how far we get today. But this is kind of the steps you'd go through for creating your own footprint libraries. It's very similar to what you did for schematic symbols, except now it's a physical instantiation. And then you actually begin your layout project by importing your netlist along with something called a technology file. And it will ask you zillions and zillions of questions, mainly what footprint to use for which component. So that's a very fun part. And then the real fun begins, which is the layout. And so from your layout, after you've created this net list, and you've created the footprints, and you've created your new project in Layout Plus, you actually have to place all of your components on the circuit board, draw an outline, and then actually route your traces around, check for errors, do post-processing so that it's ready for manufacture, and then send it out. So this is kind of the what's left to cover in the next 2.5 lectures remaining or so. So any questions about the kind of 10,000 foot view of the layout process? Yeah?
What frequency do you have to start worrying about the shape of your trace?
Okay, the question is at what frequency do you have to start worrying about the shape of your trace? It's analog. So the answer to your question is analog. It's an analog question. I can't say it's 30 megahertz. It depends on what you're doing with your system. It depends on a lot of different factors. I mean, in a couple tens of megahertz, the shapes of your traces don't matter too much. When you get to 50 to 100 megahertz and you're dealing with memories, you start to care about the lengths of your traces. And when you get to hundreds of megahertz and higher in gigahertz, you care about the shapes for reflections when you're actually having a 90 degree. But for everything you do in this class, you'll do right angle traces, so you don't have to worry about the shape too much. Yeah?
I've heard that right angle traces, if you're not doing a professional kind of board, can flake off. Is that?
All right, so the comment is that you've heard that some kind of lower grade PC boards will have right angles flake off. From my own experience, I haven't had problems with corners in particular flaking, but if you have a crappy board, just everything flakes because it's laminated down. The first place where you'll start having board problems is on your pads. So if you're soldering a very small surface mount component and you make a big mess with solder and you bridge a bunch of things together and then you clean up the bridge by heating it up again with solder wick, and then you solder the pin back down and then you make a mess on the other side and then you heat the same board up, eventually the trace will delaminate and you'll rip up the pad and the trace that goes with it. So I think that's your first failure point. I haven't, at least in my experience, noticed right angles versus 45s being any more or less susceptible to ripping. In fact, it always seems like it's the middle of the trace. Probably just bad luck. So other questions just on this? I mean, this is a very high level view before we actually start doing this by hand. Okay, and there's some other things to worry about, some of which you guys have brought up and some that I'll bring up just to give you some food for thought. So the first thing is that remember we have these bypass capacitors, these filter capacitors that you're putting next to all of your ASICs that need power. And you want to place those as close as possible physically to the pins that are actually being supplied with power. And you want the power to go in the sequence from the power source and then to the capacitor and then to the device pin. So this is where the physical thing that you see when you're doing layout is the physical instantiation of whatever it is you're doing. So remember in the schematic you can place your capacitors anywhere you want and you have no idea where they're actually going to be relative to each other in the real world. Layout is that transition to the real world. So what you do here physically has to match what you're thinking you should be doing. This is the one time where that matters. So, and we'll give demonstrations today. You want to go from your power plane or your power source or the trace carrying your power, and then have the capacitor going off of that, and then from the capacitor into the actual device pin. If you don't do this, the filter capacitors, the bypass capacitors, are not as effective as they can be. Yeah?
So in your previous schematic, you have two capacitors for each power node, right? One is non-polarized and one is polarized. Do you mean for the non-polarized, you want to place it as close as possible to a particular IC?
So the question is, if you have the non-polarized and the polarized and your actual component, what kind of order do they go in? And generally you go from the power source to the polarized capacitor to the ceramic capacitor, which is the non-polarized, and then into the actual device pin.
So you want to place the polarized capacitor as close as possible to the power source, right?
No. All three of those capacitors go right next to each other by the device.
Oh.
Your power source will have capacitance as well before you enter your power plane or your traces. But the idea of having the tantalum capacitor, for example, the polarized capacitor, right next to the non-polarized, right next to the pin, is that the device will draw a current from the ceramic. The capacitor you have locally, the tantalum, the polarized one, will refill the ceramic capacitor, and then over longer periods of time, the actual power will come from the trace to refill the tantalum. So that's kind of the waterfall of current draws, if you will.
So I got confused. So why do you want to have both the polarized ceramic?
All right. So the question is now, why do you have to have both of these capacitors? So ceramic capacitors are, you can think of as being very fast acting. They're good at high frequencies.
Not polarized.
The non-polarized. Non-polarized ceramics. But they're generally of much lower capacitance than your polarized capacitors like tantalums. So your tantalums are a little bit slower to respond, but at least they're better than having to wait for the propagation delay down a trace.
Okay.
So
it seems that we are limited by the availability of capacitors.
Yeah, so you're basically limited by capacitor technology. If you could, I have yet personally to see a reason why you would have to use tantalum and couldn't just use ceramic everywhere. There may be some reasons in some applications, but I can't think of any immediately off the top of my head. Doesn't mean there aren't applications for it, though.
How should the
So the question is, how should the polarized capacitors be oriented with the positive on the positive? I mean, you want, the polarized capacitors matter, right? Because one side's positive and one side's negative. And your schematic symbol will indicate which side's positive and negative. So that should be handled for you automatically, as long as you have the right footprint. If you have the wrong footprint, it'll be backwards. Another thing we've already kind of touched on is that the wider your trace is, the less resistance you have. That means the less voltage drop you have between point A and point B. So use as wide of a trace as you can when you can. That's especially important for power. That's also very important for signals that are very low noise or very low voltage. So if you're using, for example, some very sensitive low power analog signal, you probably want to put it on a fat trace so that you have as little resistance from your board contributing to the noise in that line, if that makes sense. There's also signal crosstalk, which is where you have current flowing in one trace inducing a voltage on another trace or a current on another trace. And that happens if your traces are really close together. Now here we're not too concerned about that. You don't have any really high current traces except for the very output of your MP3 player, the actual like going to your headphones. But a way to help avoid this is that if you have traces that have to cross, you want them to cross at 90-degree angles. Now this is crossing on different layers. They cross on the same layer, it shorts. Remember, this is the physical world now. So make sure that you keep things orthogonal, and that will cut down very dramatically on the amount of crosstalk you have. The other thing you can do, I should flip these 2 bullet points, is you can run ground traces in between your sensitive signal traces to help shield from crosstalk a little bit. So we mentioned when we were talking about the planes that you'll generally use your power and ground planes to reduce the resistance that's going across your power rails. It also adds some capacitance to your power system itself, which is a good thing. And it also helps shield signals. So that signals, if you have your power and ground planes in the middle, and you have just a top and bottom layer of copper in addition, which is what your boards will be, the ground plane is going to shield EMI, electromagnetic interference, from the traces on the top from the traces on the bottom. So it's very effective to have these planes. Now, one more comment about the planes. You also have to worry about parasitic capacitances when you get to really high frequency stuff. So I know some of you all are interested in really pushing PC board technology. So you'll realize that if you have a fat trace or a plane going below a signal trace that's grounded or that's at VCC, there's going to be some capacitance between the two. It's a parallel plate capacitor. And that's going to affect your rise and fall times on digital signals going down those traces. Again, for everything we're doing in this class, none of this stuff really matters. When you start getting to really high-speed stuff, to high-power stuff, then you have to worry about all of these issues and then some. And the bottom line is basically that high frequency makes things hard. And there's a whole lot of nuances to actually make things work right. And there are a lot of weird effects with parasitic capacitances and inductances and crosstalk and cross-coupling and all of that that you might not even think of today. So high frequency makes things hard. So with that, any parting questions before the demo? Yeah? So the question is, are you only worried about crosstalk with traces that are high current? So high current will make more crosstalk because the crosstalk is a function of current. However, you're not worried about them just with high current. So if you have very sensitive signals, or if you have anything high speed, you have to worry about crosstalk. Because remember that when you transition from a logic low to a logic high, you're transitioning from 0 volts to 5 volts. So there is some impulsive current flow going down that line. So just because it's not a high current that you may traditionally think of like a power rail, doesn't mean that there's not high current noise going through there that can cross-couple. Yeah?
And when you say ground traces between sensitive signals, do you mean that it's on the same layer, or is
Yes. So the bullet that says run ground traces in between sensitive signals, that's on the same layer as those signals. So if you have 2 sensitive signals going parallel to each other, They'll just put an extra ground trace in between the two to help shield them. If you have, for example, if you're worried about impedance matching for high-speed video systems, like if you're doing high-definition TV or something like that, you'll have to put very thick, wide traces on the same layer and on the layer above and below to match impedance of the trace in the center. So basically making a coax cable out of PC board. So there are special cases where you have to do above and below as well. Yeah?
Once you finish the layout, will the software be able to check if it's consistent with schematic?
Yes. So the question is, once you finish the layout, will the software be able to check for consistency with the schematic? And it will indeed. And we'll go through that whenever we can. It has to be either Thursday or Tuesday. Yeah.
So you say you give us details of how wide our traces can be?
Yes, so I will give you the tolerances basically for the project, which will specify the minimum trace width, the minimum trace separation, the minimum annular ring, the solder mask swell, and some of those parameters.
So how much do you have to worry about the resistance?
So the question is for this project? So the question is for this project, how much do you have to worry about the resistance? Not much. There'll be a few places where you do have to worry. You have to worry on the audio output going to your headphones. You probably want those to be fatter because that's actually driving power. You have to be careful with all of your power pins. Those all need to be as fat as you can without running into adjacent neighbors. So any other questions? Yeah.
So can we also use the power plane instead of ground plane to
To do shielding?
Yeah.
Yes, so the ground plane and the power plane are both great for shielding other layers. That's one of their functions.
But then to use both of those things, the power and the ground signals start bouncing.
So the question is, if you use both the power and the ground plane, you have some bouncing. Well, we're assuming your current's not really flowing off your board and back to an alternate ground. We're assuming you don't have a ground loop somewhere. So they'll be bouncing together, so your common mode is going to be pretty low. And the other thing is that just because you have a very large area of ground, or a very large area of a conductor even, right, you basically get Faraday shielding. So there can be some emitted noise, especially from power planes if you have a lot of different power planes, but ground planes do a very good job of shielding. But power planes do as well, depending upon your application.